Good afternoon, everyone. I will be sharing with you this afternoon my final for the Data 609 class. I worked on a Monte Carlo simulation for a blackjack game. And I'll just kind of share with you, um, what Monte Carlo is, the rules of the game for blackjack, and then I'll kind of walk you through what I did with the code. And then I'll show you some of the results that I got. So Monte Carlo is something that was used back in the 1940s by scientists that were working on the atomic bomb. It got its name from a resort town in Monaco that's very known for its casinos. Um, and as you can imagine, it's used in just about every industry from transportation to finance to any industry that you can think of. There is use for Monte Carlo simulation. And it can be used for something as simple as rolling a die to telling you the value risk of a particular portfolio. It uses random numbers to build a model of possible results by substituting a range of values for any factor that has inherent uncertainty. And then it calculates the results over and over, each time using a different set of random values. In this case, we will be creating the blackjack game, and because the cards are all worth whole numbers, the random numbers that we will be generating will all be whole numbers. So the object of a blackjack game is to get as close to 21 as possible without going over 21. Cards 2 through 10 are worth, that face value. So if you draw a 9, it's worth 9. If you draw a 2, it's worth 2. When it comes to the aces, though, it can either be an 11 or a 1, depending on, what you have already, right? So if you already have 12, you're not going to have it be 11 because then it'll push you over 21, right? The face cards like the queens, the kings, and the jacks, those are worth 10 each. For our particular simulation, we're just going to keep in mind that the player stands at 16. They're going to keep drawing until they hit 16. They're going to keep, and the dealer is going to keep drawing until they hit 17. Both of the players are going to start with 2 cards each. In a typical game, the dealer has 1 card face up so that you can kind of make a decision based on that 1 card what you want to do. But in our simulation, the player is not going to see either of the dealer's cards. We'll be using 2 cards shuffled together, and when those two decks, and when those 2 decks are gone, we're gonna keep the score and start again at 0. And then at the end, we're gonna get the average of those scores. So I created a sum function, which essentially is tallying up what the hand is, what each hand is, So after I created that function, I created a function for the player, and the components are like the hand that you're dealt, which is the initial 2 cards that you get, and then you get the cards, which is a vector of the pre-shuffled 2 decks together. I tells us the position of the most recent card dealt, and then the player strategy is, like I said, to keep going until you hit 16, and then you stand at 16. And then finally, I built the game itself, and then I played a few times. One thing that I did notice, one thing that I did put in was after each run, it would tell you the average winning per hand. Oops, I'm sorry about that. The average winnings per hand. And then here it just tells you for each iteration what the winnings are, right? So for the first iteration, you won 14. For the second, -8. For the third, -4, right? So I decided to kind of plot these to kind of see what I would get. And this is the plot that I came out with. And immediately what jumps out to me is that it looks as though it could be some form of a quadratic equation. So I wonder if there's a quadratic equation that can be fitted to this to predict what your score would be after each round. And so that would be kind of the further work that could potentially be done on this, is to um, run it a few times and plot a few different of the results and kind of see if we can get a general equation to um, predict how a score would go for a particular game. And that is it for my presentation. Thank you.